I'm a volcanologist, and I've known for a long time that major volcanic eruptions can actually have significant impacts on weather immediately and in some cases climate on the longer term. And what I became interested in is trying to put that into the context of all the possible factors that actually could contribute to climate change. And so that's what I've developed here in this particular talk. We know that since the start of the Industrial Revolution, global temperature has increased about 1.2 degrees centigrade. Extreme weather and climate events are becoming more frequent. And we also know that a significant increase in the amount of human-made or anthropogenic greenhouse gases to the Earth's atmosphere. So what I want to evaluate is these various factors that contribute to increasing global temperature and climate change, and evaluate which ones are rapid or fast and which ones are slow, because we're looking for the ones that are fast. When the Earth first formed 4.5 billion years ago, the surface temperature of the Earth at that time must have been at least 1500 degrees centigrade. Now, the Earth's core temperature is still 6,000 degrees. So there's clearly a temperature gradient from 6,000 to 10 degrees centigrade average at the Earth's surface, which means that the Earth's interior will be progressively emitting heat, losing heat to the Earth's surface. If we look at that very low flux of heat compared with solar incoming radiation, we can say, look, it's really, really low. So we can eliminate slow and progressive heat loss from the Earth's interior as a cause for the global warming that's occurred in recent times. The flux of solar radiation to the Earth's atmosphere is that the intensity of that radiation actually cycles on an 11-year cycle. But those changes actually only account for a change in temperature of 0.1 to 0.4 degrees centigrade. And of course, after each peak of perhaps up to 4 degrees centigrade, the atmosphere loses that accumulated heat. So this diagram shows in yellow there this cyclicity of solar irradiance. And then compared with that is the rate at which temperature on the Earth's surface has been increasing. There's no parallelism between those cycles. So we can say reasonably confidently that that change in solar irradiance cannot really explain the relatively recent temperature increase that the Earth's atmosphere has experienced in the last few decades. So then we get to the orbital behaviour of the Earth around the Sun. The shape of the orbit, which is an ellipse, changes shape. Another orbital behaviour that changes is that we know that the Earth is spinning, but the axis of spin is inclined at an angle of between 21.5 and 24.5 degrees to the vertical. But that changes. And then in addition, that axis also wobbles. Now, in concert, those various changes define 100,000-year cycles of changing in the amounts of thermal radiation that come from the Sun, which therefore affect the global climate and temperature. There are two graphs here. There's a red one, which is temperature change, and there's a black one, which is carbon dioxide levels. And you can see there's a remarkable sympathy between increasing and decreasing temperature and increasing and decreasing carbon dioxide levels. Basically, the carbon dioxide levels, shown on the left here, were more or less a nice balance. The peak carbon dioxide level through this natural balance was about 300 parts per million. Except, right at the end there, this is the last 250 years, where basically the carbon dioxide level overshot 300, and now the latest measure in May this year is 424 parts per million. So then we go to asteroid impact. The Earth experienced a lot of asteroid impact during its early formation stages. Perhaps one of the best studied ones in terms of potential climate impacts is the Chicxulub asteroid, which impacted the Yucatan Peninsula in Mexico just about 65 million years ago. There was an initial frictional heating, just lasting minutes perhaps. Then there was a basic interval of cooling, but also the location where that asteroid impacted the Earth's surface was dominated by limestone bedrock. And a lot of that stuff got ejected into the atmosphere, which then increased the carbon dioxide level of the atmosphere and caused an extended period of warming. So that's what asteroids can potentially do. But there has been no major asteroid to cause such effects over the last few million years. We can exclude this particular climate changing cause as an explanation for the changing temperature of the globe in the last 250 years. And now to volcanic eruptions. There's been a number of studies to calculate what the annual flux of volcanic carbon dioxide is to the atmosphere. And the figure is generally up to about 260 million tonnes. But compare that with the amount of carbon dioxide that humans are releasing to the atmosphere per year. 40 billion tonnes. The input from volcanic gases is absolutely insignificant. Now, there have been no major carbon dioxide producing volcanic eruptions in the last 250 years. So we can exclude carbon dioxide from a volcanic source as being a cause of the current global warming. Let's now look at sulfur dioxide. It reacts with a number of agents in the atmosphere to form these droplets of sulfuric acid, and these reflect solar radiation back to space. So in summary, only super eruptions are capable of causing rapid, substantial climate change. There are none that really affect global climate involving the emission of a lot of carbon dioxide. Sulfur dioxide-rich eruptions can in fact produce a lot of global cooling. None of them can explain the current heating that we're experiencing. So then we go to biological processes. So some are carbon dioxide absorbing, and these include photosynthesis. There are also carbon dioxide producing processes in the biosphere. Respiration, obviously, is a really important one from animals and plants. And then, of course, there's the decay of organic matter. These changes, however, in carbon dioxide levels through biospheric processes are reasonably slow. We can say that apart from deforestation in the last 250 years, these other processes probably haven't contributed to the very rapid temperature rise that we've experienced. So then we go to the dynamics of the Earth's atmosphere and the ocean. If we just took a simple globe, we know that the poles are cold, the equators are hot, and that should set up a simple north to south and south to north convection system that redistributes heat over the Earth's surface. Now, the thing that stops that simple convective cell redistribution of thermal energy is the fact that the Earth is rotating. This is a nice theoretical model, but it presumes that the Earth has no continents. But now we have the continents, and of course what we know is that these latitudinal oceanic currents actually get deflected by the margins of the continents. And this is the Gulf Stream here in the Atlantic. And it gets deflected along the eastern margin of North America and then along the eastern margin of Greenland and reaches the Arctic Ocean. It delivers warm tropical waters to those high latitudes, and that increases the evaporation rate of seawater in the poles, which then, of course, leads to a lot of water moisture in the atmosphere. And because of the low temperature of the atmosphere, that very quickly induces condensation and precipitation as snow, which then begins to build up snowfields and ice sheets in those polar regions. That redistribution of thermal energy from the tropics is a really important part of that story. That's all well and good, but have the continents always been in their current position? And the answer is no. Could that actually cause climate change? And the answer would be yes, if the continents are drifting across latitudes in north-south directions, okay? And if you want to calculate what the temperature effect of that northward displacement is, it amounts to 0.00029 degrees centigrade. So our climate here in Melbourne is not going to change significantly through that as a factor. A question then obviously arises, did the Earth experience climate change in the past? The answer is yes. How do we know? Because we can actually measure past temperatures using a geochemical proxy. And the geochemical proxy that is used is the ratio of the oxygen isotope 18 to the oxygen isotope 16. We can actually collect fossils of different ages back in the past, and we can analyse their calcium carbonate skeletons, separating out the oxygen, and subjecting that to delta 18 analyses. The top image there shows over 57,000 delta 18 analyses. The analyses span from just over 500 million years through to the present day. And the calculations of what the temperatures might have been in the past are on this second diagram there. These different graphs reflect different possible temperatures, and they're based on using different models that the geochemists use. Now, which one is correct is irrelevant. What is important here is that they all have the same shapes. CO2 and temperature change naturally in a state of balance until 250 years ago. And then, in the last 250 years, everything has skyrocketed. How can we really be sure that it is all anthropogenic carbon dioxide and not just natural carbon dioxide? There are 3 isotopes of carbon, 12, 13 and 14. When vegetation material or fossil vegetation material such as coal, gas and oil are burnt, it's large volumes of carbon-12 that are released into the atmosphere. And carbon-12 relative to fairly static levels of carbon-13. So basically, when we combust fossil fuels, we're lowering the ratio of carbon-13 to carbon-12. Now, what that tells us is that the rise of carbon dioxide in the last 50, 70 years, and certainly in the last 150 to 250 years, is almost entirely due to the release of anthropogenic gases. Measurement of carbon dioxide levels, methane, nitrous oxide, particularly from ice cores over the last few hundred years, have shown the following trends. Carbon dioxide going up and down a bit, but then, since the start of the Industrial Revolution, skyrocketing. Similarly with methane, skyrocketing. And then with nitrous oxide, again, exactly the same. Here's the temperature increase, particularly from the 1950s onwards today, which correspond basically with the automobile explosion. Temperature has increased and accelerated at extreme rates. I think we can unequivocally attribute rising global temperatures in the last 250 years to the burning of fossil fuels and extraction of cement and other commodities. There is value in greenhouse gases because they moderate, they mediate heat loss, heat gain, etc. from the various sources that we've discussed. It's just identifying the Goldilocks balance that allows us to have some control. And there is one way in which we control it, and that's through anthropogenic gas release and emissions.